In this lecture, I'll address the evolution of the class Mammalia. In order to tackle the early evolution of the mammals, we have to travel back in time again to the period just after the Permo-Triassic mass extinction. If you remember from past lectures, the end Permian extinction was the largest of the 5 mass extinctions in Earth history. There are many different proposed causes, and we tackled some of those earlier, but the most continually supported trigger are the massive volcanic eruptions that occurred in China, early in China, and then the largest trap eruptions to have occurred in the Phanerozoic, the Siberian traps. If you recall from the chapter on amniote evolution, which was a number of weeks ago, the dominant amniotes during the Permian, prior to the extinction event, were the synapsids. The pelecosaurs, like Dimetrodon, were replaced in the mid-Permian by the therapsids, like Thrinaxodon, which is a cynodont. Two therapsid groups survived the Permo-Triassic extinction, the cynodonts and the dicynodonts. The therapsid lineage would then survive on until the early Cretaceous, meaning that they lived alongside the dinosaurs that we covered in a previous chapter, and the pterosaurs, and the early mammalian lineage that evolved out of the cynodonts. Early mammal ancestors do not have all the characteristics that are indicative of the crown mammals that we see today. So they're classified as mammaliforms. That's a very similar term to what we learned for other groups when we used sauropodomorphs. Those are the animals that are like the sauropod dinosaurs but don't meet all the characteristics. And this is the same thing we have here. We have defined characteristics for mammals. And as we dig back into the fossil record, we see that there are a number of groups that are stem mammals that show the diversity that the mammals evolve out of. So they don't have all the characteristics of the mammals that I will mention in a couple of slides from now. So mammaliforms are represented in this image by Morganacodon. Morganacodon is an individual that was around 4 inches in length. Its skull would have been about an inch long, just for scale. They are relatively small, shrew-sized animals that, in all likelihood, were burrowers. The therapsid group here, represented by Thrinaxodon, is known to have burrowed, and I showed you an example of a burrowing Thrinaxodon that was buried, and we see them very frequently preserved that way. There are also early mammals that are found in the same sorts of burrows. So it seems extremely likely that the groups that are found between those two, the mammaliforms, are likely burrowing individuals as well. It's also very common for animals of this size filling this niche. Early mammals were likely nocturnal, because those groups that in the modern world that fill the same environmental roles are also nocturnal today. So we can assume, until shown otherwise, that the mammaliforms, like Morganacodon, were nocturnal animals that had the capacity to burrow. The earliest mammal-like groups evolved from the cynodont and an acynodont ancestor, somewhere in the order of around 225 million years ago. A good representative of these animals would be Adelobacillus. So Adelobacillus is represented on the right-hand side, scaled down to a human hand, with the recovered fossil skull in the upper right. Adelobacillus is only known from a partial skull that was recovered from a formation in western Texas. It has distinct cranial features, though, especially the housing for the cochlea, the inner ear, that suggest that it's transitional between the cynodonts and the mammals. It has ancestral characteristics of the cynodonts in the skull, and then also derived characteristics of the mammals that we see. So for this reason, it's thought to be, if not the common ancestor, at least one representative of the common ancestors of modern mammals, and at the very least, a relative of that ancestral mammal individual. Though traditionally classified as a mammal by trait-based taxonomy, it falls outside the crown group containing all true mammals. So if you remember that terminology, crown means an individual group that we see in the biological world today, defined back to its earliest representative that holds all the true characteristics, derived characteristics of that individual group. And so Dilobacillus is not a crown mammal, but it would be a mammalia form individual and probably led to the evolution of the mammals. So what you know is that Dilobacillus is a good representative of that group. And at 225 million years old, it is the oldest representative that we see in the fossil record today. So, as far as the mammals are concerned, the derived characteristics, I think, should be easier to remember than some of the other groups, partly because they're present in your body. Being a mammal, we can look into our own biology to see the derived characteristics of this group. As far as the derived characteristics are concerned, we define mammals as having a single bone in their lower jaw. One dentary bone, that's the name for the bone, the dentary bone, makes up the mandible, as opposed to animals in our ancestry like the pelecosaurs, which have a much more reptile-like jaw. They share similarities with the diapsids that are cousins of theirs on the family tree. And so the synapsids would have had 4 bones in the lower jaw. So in the bottom right-hand corner is a sketch of a non-mammalian amniote, or an early amniote that doesn't possess the same characteristics. Or you could take it as a modern-day reptile, which is an amniote non-mammalian. In this case, you can see that it still has a dentary bone. That's the dentary bone is named that because the dent refers to the teeth. So that's the bone that allows teeth growth to take place. In reptiles, including the dinosaurs that we talked about a chapter ago, the angular bone sits underneath the dentary bone, and they're attached. They're fused together, just like other bones within the skull are fused together. Those 2 bones make up the mandible, and at the very back of the mandible is called an articular bone, and as its name denotes, the articular bone allows articulation between the mandible and the skull. And then on the skull side of the jaw, on the opposite side of the joint, there's the quadrate bone that houses the joint that the jaw locks into. And then the rest of the skull, housed around that, would be called the squamosal bone. In the upper corner, we have an early mammal representative, which is a derived mammal, so it has all the right characteristics. Its bottom jaw, its mandible, is just the dentary bone, still produces teeth, but its joint is between the dentary bone and the squamosal bone. And we have the migration of the remaining 3 bones that we'll talk about in a future slide that have moved into and are repurposed as bones within the inner ear. And we'll talk about that movement in just a little bit. The other thing that mammals have as far as derived characteristics are they have a variable toolkit of different teeth in their mouths. I began that discussion earlier in the semester when we talked about the pelecosaurs and mentioned that they had the variability in tooth shape. Mammals take that to the extreme, so we have incisors, flat nipping teeth in the front, canines, puncturing and tearing and shredding teeth on the sides, and then molars and premolars in the back that are well adapted for grinding our food and pre-digesting it. As far as the mammals go, their mode of birth is we abandoned the production of eggs and we give live birth. There'll be 2 different methods for live birth in 2 of the groups of mammals. And then we'll have to call out the fact that live birth can't be a true derived characteristic because monotremes are mammals, but they lay eggs. So we'll go over that in a later slide. The mammals are also famous for having mammary glands. That's the root name for mammals, the possession of glands that produce milk that suckle their young. So our young are raised and parented by the mammalian parents. And one of the things that we're able to do is feed our young without going out and hunting and bringing food back to a den. So the young are feeding off of the mother who is able to produce milk in this case. Mammals are also endothermic and homeothermic. We've talked about that transition. The cynodonts appear to be producing hair early in their stage, early in hair production. They have whiskers. And then the mammals themselves evolved the capacity for endothermy and homeothermy, or they are warm-blooded, to use the old term. That warm-bloodedness means that they have a constant body temperature and a high metabolism that allows that body temperature to stay the same, which means that they have to feed more often to fuel that metabolism. In order to be more fuel efficient, so to speak, mammals are covered in a coat of hair, and that hair helps trap heat and insulate the individual so that they can maintain a constant body temperature. So those are some of the early derived characteristics of the mammals that we see in the crown group. And I want you to remember all of those for the quizzes and exams coming up. As far as the list, we're going to step through the bones of the jaw, changement in the muscle placement of the muscles that operate the jaw, the teeth that are in the jaw and how they adapt and change. And then we'll move our way back to the ears because that's a connected system. And from the ears, we'll move on to developments within the brain and live birth and endothermy last. As far as the jaw is concerned in mammals, for reasons that we don't fully understand, a number of lineages of synapsids, including the synodont therapsids that give rise to the mammals, began to evolve shifts and changes in placement in the jaw joint. So while we may not completely understand why this change in the bones within the jaws are taking place, there's a good fossil record for it. These are just key moments in the fossil record present on the right-hand side, but it shows the slow but steady shift towards the current morphology of mammals that we see today. On the bottom, we have animals from the Carboniferous that have very reptile-like jaws. So the early synapsids had jaws that were representative of the rest of the amniote groups. They have the articular bones and the dentary bone highlighted in pink and white here, and then the articular is yellow and the quadrate is blue. So what you're looking for is you don't need to remember all these individuals and what happened, but the bones that are non-dentary are shrinking in the evolutionary history of the mammal ancestors as they move towards the back, and the dentary bone is becoming the dominant bone within the jaw. And then after the development of the therapsids and the early mammals, we see the bones are finally pushed from the back of the mandible, back of the lower jaw, up and into the ear. And that requires an awkward transition because we have to move the joint. And moving a joint evolutionarily can't happen really rapidly. It has to be slow, and there has to be some plausible way for the mandible to still be jointed within the skull in a population of individuals that shows variability there. Probenignathus is an individual that has a good preservation of the bones in the skull that show how we transition this joint. If you look at Probenignathus, which is the individual being shown down at the bottom there, the dentary bone makes up most of the mandible, as you would expect in an animal that's transitioning and evolving into something similar to the mammals. And then we have the articular bone highlighted in red, and the quadrate bone highlighted in orange. And what you see is the articular bone loses most of its contact with the jaw in Probenignathus, and the dentary bone instead is contacting a socket that's partly housed within the squamosal bone and partly within the quadrate. And then from there, it's a small scale shift to just exclude the quadrate bone from that joint and have it just be a joint between the dentary and the squamosal bone. So there is this slow and gradual change over a period of a few 100 million years between the evolution of the synapsids and their very reptilian-like jaw up through the much more simplified jawbone of the mammals, with the dentary bone dominating the entire structure. So one of the other shifts that takes place alongside the changes in the dentary bone and the jaw and skull joint is the splitting of the muscles that attach to the dentary bone, to the mandible. In the case of the mammals, we see a division between, and actually in a mammal ancestor, we see a division between the temporalis muscle that I pointed out in an earlier lecture that sits where your temple is. You can flex your jaw and feel that muscle flex, push your fingers away. And then the masseter muscle, there's a secondary muscle that attaches up and under your cheekbone and then down in the back of your jawbone. I said if you clenched your jaw, right where the angle in your jaw is, if you put your fingers on there and clench your jaw, you can feel them pushing away at your fingers. The masseter muscle probably originally served to hold the lower jaw in a cradle of muscles and helped with chewing. So the changes in size and placement of the masseter muscle are what ultimately shifts where the teeth meet and how they occlude. So in a dentist terminology, occlusion is how the teeth meet and grind together. We can think of an extreme member, a snaggle-toothed individual of a fish with sharp snaggle teeth. The teeth don't need to meet in any way, shape, or form. They don't have to have occlusion in any way. Instead, what happens is those teeth just randomly hook on or stab into prey and just need to be abundant enough and in random enough directions that they can capture prey and then swallow it. So the teeth effectively don't need to meet up or point towards each other or have any sort of relationship between the upper and lower jaw. In mammals, what we see is a very precise placement of the masseter that allows the back teeth, the molars, and the front teeth to hit very precisely. So that is an exceptional occlusion, meaning that our teeth grind very precisely, and we're going to see that leads to a lack of replacement. Whereas reptiles in the modern world can shed teeth. Fish that have teeth, sharks for example, shed teeth continually and then are always replacing them. Mammals only get one shot at it, right? You have what are called your milk teeth or your baby teeth that you have as a child, and then sometime around 7 or 8 years old, you start shedding those. And by the time you hit adolescence, you've replaced all of them with your adult teeth, which are then in your mouth for the extent of your life. The order of mammals, somewhere in the tens to nearly 100 years, you're using the same teeth. That seems like a disadvantage, but in fact, that precise occlusion allows you to chew and grind your food very accurately. So you're much better at pre-digesting your food than an animal that doesn't. So the advantage to having those teeth for a full lifetime is that they meet up very nicely. You can see that in practice when you go to the dentist and they give you a cavity or a crown or replacement on a tooth. They spend a lot of time trying to make sure that that tooth matches up with the tooth above it, because you don't want that tooth to hit first and keep your other teeth from grinding together, or you don't want it to be a gap to form between the two. Otherwise, they won't be very functional. They won't be grinding the food in the way that we're supposed to. So the movement of the masseter muscle is related to the replacement of your teeth throughout a lifetime and the types of teeth that we have. As far as mammals are concerned, we see a pretty progressional evolution within the teeth, particularly the molar teeth. Mammals produce very unique molars. All modern mammals have the tooth type that's present on the right-hand side of your screen here, what are called tribosphenic molars. They are a mammalian signature. Prior to the development of that, animals that are in the mammalia forms had complex molars, but not nearly as complex as modern mammals. So Morganocodont has what's called a triconodont tooth. And tri, of course, means 3. Cone always refers to the shape, the coner shape, and then dont is a tooth. So in this case, there are 3 cone shapes to the teeth. Triconodont means there are 3 peaks. On the upper row in your image here, you're looking at the side view of a tooth. And then in the bottom row, you're looking at a top-down view with the primary cusp on the tooth highlighted in red and secondary cusps highlighted in blue, or what are called accessory cusps. So the primitive mammal-like animals, the mammalia forms, have these molars that are triconodont, and they're pretty good for cutting and shredding their food and for producing decent pre-digestion. These animals, then what we see is a shift in animals like Cunitherium, which is slightly more mammal-like and less mammaliform. Its molars evolve away from having a centralized cusp. The accessory cusps drift out and away from the tooth, meaning that there's a broader platform with 2 smaller cusps on one side and a main cusp offset. That gives you something that looks more similar to the molars that you and I have today. And then eventually we replicate that entire package so that the modern mammal tooth has 2 sections to it. The molars have what is a cutting trigonoid tooth, so it's very similar to Cunitherium's tooth. 3 cusps all housed together. And then through a fractal replacement, where we just hiccup and copy the front of the tooth on itself, we have a crushing talonid, which is a 3-cusped forefront to the tooth that has smaller height to those cusps. The front of the tooth crushes, and the back of the tooth chops and cuts. This is an effective technique, especially for small animals, for eating things that have hard parts to them. So insects are one of the main food resources for early mammals. They are feeding off of anything they can get their hands on. So insects, worms, grubs, all kinds of things. But if you have a hard exoskeleton on your food, you need to be able to crunch through that and cut it up in order to get through the food that's actually easily digested, because you don't get much in the way of nutrition or energy out of the exoskeleton of an insect. So as far as the mammals are concerned, all modern day mammals have triple molars. What we're going to see is there are three major groups of mammals. Two of them have a shared ancestor that have this tooth shape, and one has a shared ancestor with the other mammals that did not have them. So they must have convergently evolved very similar tooth shapes as far as their molars in the back of their mouth are concerned. One of the other shifts that's related to the development of the jaw within the mammals is the evolution of the mammalian ears. And it sounds odd to think that you are talking about ears in a discussion on the mouth and the jaw, but in reality, those structures are not detached. The jawbone is one of the bones and one of the morphological structures that helps you hear. And indeed, if we looked at groups that we've talked about earlier in the semester, the reptiles, animals like a crocodile will use their jaw to listen. So they ambush their prey by hanging out on the edges of waterways, and they need to be able to sense when an animal comes near the edge of the waterway. The water is murky enough that you can't see the predator hanging out there. Otherwise, it's not a very good place to hide. And when a prey like a zebra comes up to take a drink, or a wildebeest, it causes vibrations. And what the crocodile is doing is sitting there, resting its mandible on the bottom of the stream bed, waiting to pick up those vibrations. So it's listening by feeling for vibrations in its jaw that are connected to its ear. So it isn't completely crazy to think of bones in the jaw evolving and being repurposed and adapted into the inner ear. It's what natural selection does, right? As we have small variations in a population, anything that provides a positive kickback can be restructured and repurposed throughout multiple different lineages along the way. On the left-hand side of the image here, we have a reptilian ear structure with the membrane of the ear being pretty close to the outer edge of the animal's head, and then a connection between the inner ear and the outer ear with just the stapes bone. And the stapes bone is transmitting waterborne low-frequency sound really well towards the inner ear. The mammalian ear has these extra bones that are, again, adapted and repurposed bones of the jaw. You could see that in very great detail in the previous slide. So the malleus and the incus get added to the system, and the malleus is in this case the prearticular and the articular bones, two of the bones of the jaw that get readapted, and the stapes is still the stapes. The quadrate bone becomes the incus bone. So we get three bones in the inner ear, and the eardrum is usually housed farther within the skull, and it's really well adapted for hearing what are high frequency airborne sounds. We think that in early mammals, these small organisms that are shrew-like and are feeding off of insects, that a reasonable explanation for why this reorientation is beneficial, why it's a good adaptation, is that it allows you to hear high-pitched airborne sounds. And there's no way to test whether those animals were using that to hear insects. But if your major food resource, according to your teeth, is things like insects, and your ears are well adapted for hearing high-pitched airborne sounds, then it's a sound argument to make that these animals are adapting to be able to hear their prey better. I always use the example of if in the classroom or if in your room while you're listening to this lecture, there's a mosquito buzzing around, you can't not listen to it. You're going to hear that noise. Your ears are very well adapted for hearing those frequencies. I have a number of children at home, and sometime between the ages of probably a few months old and 4 or 5, they produce such high frequency noises at such volumes. I think I've lost a lot of the ability to hear these sounds. That and old age has taken it away from me. I would be a terrible early mammal. The other thing that you need if you're going to adapt your brain or adapt your to these new processing of sounds and seeing the world around you in different methods, which we're going to see that the mammals and indeed the primates, which we're going to zero in on, have brand new ways of interpreting the information that's coming in from their sensory organs. What we see in mammal brains is the development of a new section of the brain, a frontal lobe of the brain, highlighted in our little early mammal shrew-sized ancestor here, highlighted in bright pink, with the remainder of the hindbrain sitting there in sort of a duller colored pink. So that bright pink area is called the neocortex. It's the portion of the brain that is distinctive within mammals. And this is going to become really important because in humans, we explode that part of the brain. The development of the human skull is an expansion of the neocortex forward, so that some of our early ancestors had these massive brows. And in Homo sapiens, we have a pretty flat forehead, because the brain has been pushed out and the brow has fallen backwards, and that ends up losing most of that distinct brow that we see in early human ancestors. So the neocortex, there's a very similar portion of the brain that evolves and is adapted in birds. So birds have the closest thing to a mammal-type neocortex. That's a convergent evolutionary characteristic. Processing of these materials within the animal brain happens in the same central location in the front of the brain. So it isn't that bizarre that animals like the birds, which are endothermic and homeothermic active hunters and fill some of the same roles that mammals do, that they would evolve similar structures to their brain as what we have. In the human brain, the largest portion of the neocortex is known as the cerebral cortex, which is multi-layered and is known to process the types of sort of higher order functions that we think of in the mammal brain. So the generation of and perception of sensory perception, cognition, motor commands, spatial reasoning, language, all of those types of things are being processed within the neocortex. If you ever heard of the use the term like medical loosely there, medical process of a lobotomy, what they used to do is take an ice pick like device and hammer it up through the relatively thin bone of the back of the ocular bone. So they'd hammer it through your eye socket and up into the front of your brain, and then just wiggle it around a little bit and chew up that physically cause brain damage to the front of the skull to treat certain types of mental illness, and particularly aggression. You could take a person who suffered from some sorts of extreme aggression and make them completely docile by blending their brain up with an ice pick. Modern medicine. It's amazing. As far as the mammals go, we also reproduce differently than the other groups of amniotes. The amniotes are known for the amniotic egg, and what the mammals do is internalize that egg, sort of. So 2/3 of the groups have adapted the ability to give live birth as opposed to the ability to lay eggs. So I listed that as a derived characteristic, but then I qualified it saying, well, there is still a discovered group of mammals, the what are called the monotremes, that still lay a little leathery early amniote-like egg. They have the ancestral characteristic instead of the derived characteristic, although we do qualify them as full-blown mammals. It's possible that their ancestors had live birth and that they lost it and gained the ability to lay eggs again. Or the earliest mammaliform animals were still laying little leathery eggs, and the other two groups, the marsupials and the placentals, adapted live birth, and the monotremes maintained egg laying. Those are the two possibilities. We don't have fossils to show which of those is correct. The three groups of mammals and their methods for reproduction are pretty interesting. Probably the least well known as far as the public is concerned, and individuals who have never studied them, the monotremes, their mode of reproduction is the most different from what we think of for mammals. The sort of poster child for the monotremes is the duck-billed platypus. There's also the spiny echidna within that group. And these animals are so bizarre, especially the duck-billed platypus, that when they were first discovered in the late 1700s by Western culture. They'd been known about by Aboriginals who lived in the area for thousands of years. But in this case, when Western culture got there, they couldn't believe the stories about what these animals were like. So a survey was sent out to try to find an example of a duck-billed platypus. It was being described by an individual named George Shaw in Britain. And when they sent him back the hide of the animal, because that's how you collected them back then. You didn't worry about trying to transport a living individual and keep it alive. You just killed it and then sent it back to the individual who, in this case, the scientist who was describing it. He just assumed it was a hoax, that it was one of these sort of mythological creatures like mermaids that were being produced by stitching bits of fish and monkey together, making weird organisms. Some of them were really intricate and really well done. So he just kind of assumed that this bill on a weird mammal looking thing with a spike on its foot, that it must have been a ploy to sell these bizarre creatures. And so he sliced away very delicately at the back of the bill to try to find the stitches where it had been sewn onto the front of this animal's face. And he didn't find any, and verified that Ornithorhynchus is its appropriate name, or the duck snouted animal. So the duck-billed duck is coming out of the ornith, or bird, name for it. So the Ornithorhynchus is the name for the duck-billed platypus. And he not finding that it was a fake, Dr. George Shaw identifies it, names it. He gives it the name Platypus anatinus, but platypus is actually already utilized for a beetle. And so we had to throw that name out and reappropriate and use a different name for it, which is Ornithorhynchus later. That's how science works. If you work in disparate fields like beetle identification and mammal identification, you may never know that somebody already used the name that you independently came up with. And ultimately, if you did use that name second, your name gets thrown out and you have to come up with something else, or someone in the future does. You may not even know that it happened. As far as the platypus was concerned, people were interested in how they bred and how they reproduced, because the Aborigines said that they laid eggs. And of course, mammals don't lay eggs, so that can't be the case. There was a investigation that was sent out in the late 1800s to try to find the nests of these animals. They're pretty reclusive and they're small, and there's only a few places in Australia where they're present, and so you're hunting along the edges of these streams looking for little burrows and dens where the platypuses lived. And they found them, and the individual, William Hay Caldwell, was the person in charge of trying to find these dens. And he sent probably the most efficient, most science nerdy message back to London. So if you think by telegraph, you pay per word. It's pretty expensive. And so in this case, it's beneficial. All these crazy words that we use in science allow us to be very efficient in our terminology. So what he sent back was a 4-word telegraph that said everything everybody needed to know about his discovery. Monotremes oviparius ovum meroblastic. That statement meant the monotremes, in this case the duck-billed platypus, lays eggs, and that egg is meroblastic, and therefore not like bird eggs, but a different structural morphology. So he learned a lot about the eggs of the platypus, and he then sent that back in what is probably the best telegraph, and the only telegraph that you'll see in my class. The other two groups of mammals we're much more familiar with, the marsupials, and represented by the opossum here that went viral on the internet, probably 10 years ago, just because I had cross eyes. It's adorable. If you've ever met an opossum, the adorable is not the word that you use. They're fantastic animals. They keep tick populations down. They do great work, but they're not pretty or pleasant to hang around. As someone who grew up in the country and has had a number of interaction with these possums, they're aggressive, but with no bite to their bark. They hiss loudly to try to get you to go away, and that's about the show they put on. So as far as the marsupials are concerned, they're a part of the division of mammals that we call the therians and the monotremes. So the monotremes lay eggs. The therians, which means the beasts, are true live birth mammals. That's the marsupials and the placentals. We call the marsupials the metatherians and the placentals the eutherians. So the not quite true beasts and the true beasts is how those are interpreted. The marsupials give early live birth, and then the placentals give late live birth. I probably discussed the placentals a lot less because, you should know how mammalian reproduction works. You are or how placental reproduction works. You are a placental mammal. So we hold those individuals, our offspring, in for a long time. We grow them and they develop internally for a long period of time before they're born. It gives them a high success rate post-birth. It limits how many you can have. That's true of all the live birth mammals. It's more difficult to produce huge broods. You can't lay hundreds or thousands of eggs like you can if you're a turtle or a crocodile. So in this case, like humans, we only produce one offspring. We grow it for 9 months, and then it's born as late live birth. The marsupials, on the other hand, reproduce, and then the offspring are born basically in an embryonic state. A little fetus is birthed, which makes the birthing process very low risk. But the sort of transport of the individual to its developmental pouch is very difficult. That little fetus crawls through, it has bizarre footage. It's the ability to crawl through the hair of the mother and up and into a pouch where it latches onto a teat. So as far as all the mammals are concerned, they feed their young by suckling them. For the human in the bottom right-hand corner, who is my daughter, it's just an absolutely ridiculous picture of her. That's why I use it. She looks like she's drunk and ordering that one last margarita that she shouldn't. In this case, she was a breastfed child, and so that's how placental mammals feed their young. In the marsupials, it's the same. They have teats, just like in the placental mammals, and the little embryo latches onto that teat. It's almost as big as the animal when it gets into the pouch. It latches on, and then it just stays there for a number of weeks and develops in what is effectively the external equivalent to the human uterus, or to the placental uterus. So this external pouch is where the animal grows. And the benefit to that is that once the animal is capable of leaving the pouch, it can actually still go back. So if you've watched a joey for a kangaroo exit a pouch and then climb back in again, they stay for longer than potentially the mother would like. As far as the monotremes are concerned, they don't have teats. They don't possess specialized structures near their mammary glands that allow the animals to latch on. Instead, with the duck-billed platypus and with the spiny echidna, the animal produces the milk and it mats into the hair, and then the young feed off of this produced milk by suckling off of the hair itself, little mats of hair that are milk rich. They get their milk from that. There's two possibilities there. Either all early mammals had teats that the young suckled off of, and that allowed them, the monotremes, to evolve away from it because for some reason there was a benefit to not having those teats. Or the earliest mammals, the mammaliforms, all did this process of sweating the milk into their fur, and then eventually centralized locations like teats evolved because there was a big advantage for latching on. All of those are the two possibilities for the development of suckling within the mammals. As far as why this nurturing technique for raising your young evolves, it's thought to be related to egg production. As you are laying eggs, it's good to keep them warm. So an endothermic mammal roosting on top of, or early mammal roosting on top of eggs, would be a great source of heat for those eggs. But you also want to keep them coated, and what we think these animals did was the equivalent to sweat glands that you're familiar with, produced this substance that helped to coat the outer edges of the egg. When the animals hatched, when their offspring hatched, if they could then lap at that or feed off of it, it would be a great food resource. And there would be a catastrophically positive kickback to feeding off of that product that was in no way, shape, or form meant for the offspring. It was meant to help condition and keep the eggs healthy, but then becomes a backward kickback for animals, and you develop this process of suckling. That's an untestable and probably unfossilizable concept, but it's at least a reasonable explanation for how we can see the mammary glands developing into the structures that we see today. So as far as egg laying versus live birth goes, there are some modern examples that show a flip-flopping nature to this process. It isn't that weird to think of egg-laying animals adapting into live birthing animals, or retreating back and becoming egg layers again, if that's what happened in the monotremes. We look at the yellow-bellied three-toed skink here. It's a skink that lives in New Zealand. New Zealand's a spectacular country. It has coastal regions that are very tropical in climate, and then some within a relatively close lateral distance, you can get to really cold climates in the mountains. So the yellow-bellied three-toed skink is a reptile, but you can see this one has its offspring housed within its body. I don't even know how it's walking around, but this mother is pregnant, and it's going to give live birth to its offspring. That's not completely unheard of in the reptiles. There are snakes that do this. Other animals that lay eggs, typically like fish externally, there are some that give live birth, members of the shark group. So the yellow-bellied three-toed skink, what's interesting about it is that it can vary its ability to give live birth versus laying eggs, depending on where it is. So as far as the skink goes, if it's in harsher climates, colder, higher elevation climates, then it tends to give live birth. There is a higher success rate. The individuals that give live birth are selected for, and so the population drifts towards individuals that have the capacity for live birth. When you're in more pleasant conditions down near the coastline where the climate is more appealing, the animals drift towards egg laying, and the live birth is much less common. The reason for that is that there's a cost trade-off to live birth. Live birth means you're more successful. Those eggs are not going to be left at the sort of whim and will of the climate and the weather. Instead, they're protected and they're born live, sort of ready to go. The trade-off for that, though, is that the mother pays the price. The individual growing those animals internally is sacrificing its health for the production of those offspring. For example, we talked about in the evolution of the egg that the offspring, as they're developing, sap the calcium from the egg, which thins the shell to build their bones, and then they hatch from the egg. In amniotes like mammals, in a human, for example, as a fetus is growing, it still needs calcium. It gets some of that from the mother's diet, but it's also taking some of it from the mother's bones. So we leach calcium from a pregnant mother's bones in order to produce the bones of her offspring. There's some romantic connection there between a mother and child. But ultimately, it's a huge health impact on a parent to produce an offspring, on a mother to produce an offspring. So in this case, in our yellow-bellied three-toed skink, that offset, if the climate conditions it, that offset is worth paying, so to speak, if your offspring are more likely to survive. It's going to be a successful reproductive technique if there are conditions that make it successful. If those conditions disappear and there's no harsh climate, then egg laying is just as successful, and it doesn't require you to pay the price of maternal growth of live young. So the yellow-bellied three-toed skink is a fantastic example of transitions in the modern world in a single organism between egg laying and live birth. Then, as far as the mammals go, one of the things that I always do is try to address the very earliest members of groups. So, for like a Dilobacillus, for an early mammal-like animal, we also look at where are the earliest members within the three groups of mammals. And so I have this slide for you that shows the different groups of fossils that represent the oldest of each member of the mammal group. What we know is that once we see differentiation. The very earliest placental mammal, for example, appears 160 million years ago. The three groups must have appeared by then. So there are ghost lineages in the other two groups, because I don't have fossils that are that old. But they must have existed. We just don't see them until later in the fossil record because they haven't been found yet or because they weren't preserved. So as far as the placental mammals go, you and I, our oldest mammalian ancestor in the placental group is an individual named Jura Jura for the Jurassic, the time period it was found in, and Maya for mother. So this is the Jurassic mother. And it is the oldest known placental mammal. It has characteristics within the teeth that show placental development. It is only the front half of the animal. Here we have the fossil. You can see its jaw and the teeth preserved there, and its little hands and feet and ribs. That's Jeremiah. Again, this is a little guy. That's a centimeter right there. So it's a couple of centimeters long. It's a small shrew-like animal, like most of the early mammals were. As far as the marsupials go, the oldest marsupial is Sinodelphes. It's 140 million years old, so 20 million years younger than the oldest placental mammal. And it is present in here as a full articulated skeleton. So died and preserved. You can see the hair included in the fossil. Pretty well preserved. One of the things that we see there are these epipubic bones. That's one of the structures that can help you distinguish between which group of mammal am I looking at. The marsupials keep those. They're two bones that project off of the pubic bone and forward towards the front of the animal. So like that little V shape in the bones there is something to look for. Monotremes have that as well. The oldest monotreme we have is only 105 million years old, so their history is well hidden. They're probably less common, and they're also smaller and more delicate, so we just don't see them. And in fact, Steropodon is only preserved as a portion of a jaw, but the teeth are very characteristic of the monotremes. So Steropodon is the reconstruction is exaggerated. We're showing it like a duck-billed animal, even though all we have is the jaw itself, but I do know that that's an early monotreme jaw. So what you should know for a quiz or an exam is each name, what's the oldest individual for that group, how old is it, and that's the questions that I will ask you off of that slide. As far as the mammal cladogram goes, what we see are a whole bunch of other groups, the multituberculates that are in the chapter in your book, and that I don't cover, the eutriconodonts, the symmetrodonts. Those three groups evolve between the monotremes and the marsupials and placentals, or the therians. The therians all share the tribosphenic molar, and so because they have a common ancestor, marsupials and placentals both have a tribosphenic molar. We also see tribosphenic molars in the monotremes, but the ancestors of the theria do not have them. So the monotreme molar evolved differently, separately, than the therian molars. So they're a similar structure, but evolved separately for different purposes. So that's convergent evolution. The tribosphenic molars are a convergent structure within the mammal lineages because these other three groups don't possess that. They have either triconodont or other tooth structures within their back molars there. Those groups, by the way, are the three groups of mammals that go extinct at the end of the Mesozoic. When the Cretaceous extinction event hits, mammals are not left unscathed. The monotremes and the placentals and marsupials make it across the boundary, but those three other groups end up dying out, and we lose them to the extinction event. So, in the next lecture, we're going to talk about that Cretaceous extinction event, some of the causes, and what some of the groups were that were affected, and how we know that.